So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying in some kind of bed or maybe a couch, and your body is pressing down into it. You can feel that, right? That gentle pull, that weight. And you probably don't think much about it because gravity is just there. It's the most obvious thing in the world. Drop something, it falls. Simple. But here's what's strange. If you ask a physicist why that coffee mug falls when you knock it off the nightstand, they can give you an incredibly precise answer. They can calculate exactly how fast it accelerates, predict the exact arc it traces through the air, tell you the precise moment it hits the floor. Gravity is one of the best understood forces in all of science in terms of what it does. But if you ask that same physicist a slightly different question, not what gravity does, but why things have mass in the first place, why that mug has the weight it has, why matter is heavy at all, well, for most of the 20th century, that question would have made them very uncomfortable, because they genuinely didn't know. And the answer, when it finally came, turned out to be one of the strangest, most beautiful, most confusing ideas in all of physics. It involves an invisible field that fills every corner of the universe, a particle that took nearly 50 years and the largest machine ever built to find, and a handful of quiet, stubborn theorists who figured out the math decades before anyone could prove they were right. That's what we're going to talk about tonight. The Higgs Boson. The Higgs field. The whole tangled, wonderful story of how humanity figured out where mass comes from. And I promise you, we're going to take it slow. There's no rush. If you drift off somewhere in the middle, that's perfectly fine. That's kind of the point. But if you stay with me, I think you'll find this is one of those stories where the more you understand, the more astonishing it gets. Let's start at the very beginning. And I mean the real beginning, not with the Higgs boson itself, but with the problem it was invented to solve. Because the Higgs didn't come out of nowhere. It came out of a crisis, a deep, frustrating crisis in physics that had been building for decades by the time anyone thought of it. So picture the early 20th century. Physics is in the middle of the most extraordinary revolution in its history. In the span of about 30 years, between roughly 1900 and 1930, the entire foundation of how we understand reality gets torn up and rebuilt. First, there's quantum mechanics. This bizarre, counterintuitive framework that says particles can behave like waves, that you can't know a particle's position and momentum at the same time, that the universe at its smallest scales is fundamentally probabilistic. Then there's Einstein's special and general relativity, which reimagines space and time as a single fabric that bends and warps in the presence of mass and energy. These two revolutions, quantum mechanics and relativity, are arguably the two greatest intellectual achievements of the human species. And they both work spectacularly well. Quantum mechanics explains atoms, chemistry, electronics, the behavior of light. Relativity explains gravity, the motion of planets, the expansion of the universe. The problem is, they don't play nicely with each other. Think about that for a second. You've got two theories, both confirmed by experiment over and over again, both making predictions accurate to absurd numbers of decimal places, and yet when you try to combine them, when you try to write down a theory that is both quantum mechanical and relativistic at the same time, things go haywire. The math produces infinities, nonsensical answers, predictions that say the probability of something happening is infinity%, which is obviously meaningless. Now, this was a real problem, because physicists knew that the universe doesn't care about our theoretical convenience. the universe is both quantum and relativistic. Atoms exist inside gravitational fields. Particles move at speeds where relativity matters. So there had to be a way to make these two frameworks coexist. And starting in the late 1920s and accelerating through the 1930s and 1940s, some of the most brilliant minds in physics set about trying to do exactly that. The goal was to build what's called a quantum field theory, a framework where the quantum world and the relativistic world are unified into a single, consistent mathematical language. And here's where the story gets human. Because this wasn't a clean, triumphant march toward truth. It was messy. It was full of wrong turns and arguments and people throwing up their hands in frustration. One of the first people to make real progress was a young Englishman named Paul Dirac. Dirac was extraordinary. Quiet, precise, almost eerily logical. There's a famous story about him at a dinner party where someone made small talk by saying, "It's windy outside," and Dirac got up, walked to the door, opened it, looked outside, came back, sat down, and said, "Yes." That was Dirac. He didn't waste words. But what he did with equations was breathtaking. In 1928, Dirac wrote down an equation, the Dirac equation, that described the electron in a way that was fully consistent with both quantum mechanics and special relativity. And this equation was beautiful. It naturally explained the electron's spin, a quantum property that had been mysterious up to that point. But it also predicted something nobody expected. It said there should be a particle exactly like the electron, but with a positive charge instead of a negative one. An anti-electron. Dirac himself wasn't sure what to make of this at first. Some people thought it was just a mathematical artifact, a glitch in the formalism. But then, in 1932, a physicist named Carl Anderson, working at Caltech, was studying cosmic rays, high-energy particles that rain down on Earth from space. And he found it, a particle with the mass of an electron but a positive charge. He called it the positron. Antimatter was real. Dirac's equation had predicted something that nobody had ever seen before, and it turned out to exist. That's the kind of moment that makes you trust the math, even when the math tells you something bizarre. So Dirac's equation was a triumph, but it was also just the beginning, because the electron isn't the only particle in the universe. There are protons, neutrons, photons, and, as physicists would discover over the coming decades, a whole zoo of other particles. And the question was, could you build a complete quantum field theory that described all of them and all the forces between them? Let's talk about forces for a moment, because this is important for understanding why the Higgs matters. In everyday life, you experience forces all the time. Gravity pulls you down. When you push against a wall, the wall pushes back. That's the electromagnetic force, the repulsion between the electrons in your hand and the electrons in the wall. There's also the force that holds the nucleus of every atom together, which is called the strong nuclear force, and another force responsible for certain kinds of radioactive decay, called the weak nuclear force. 4 fundamental forces: gravity, electromagnetism, the strong force, and the weak force. That's it. Every push, every pull, every interaction in the entire universe comes down to some combination of those 4. Now, in quantum field theory, forces work in a very specific and honestly kind of wonderful way. 2 particles don't just magically push or pull on each other across empty space. Instead, they exchange other particles. Think of it like 2 people standing on ice. If one of them throws a heavy ball to the other, both of them recoil. The thrower slides backward, and the catcher slides backward when they catch it. The ball carries momentum between them, and the result looks like a force pushing them apart. That's a rough analogy, and it breaks down if you push it too far. But the core idea is right. Forces are mediated by the exchange of particles. For electromagnetism, the particle that gets exchanged is the photon, the same photon that is light, that carries energy from the sun to your face, that bounces off this room's walls and into your eyes. Every time two charged particles interact, they're tossing photons back and forth between them. For the strong force, the exchange particles are called gluons. For the weak force, they're called W and Z bosons. And for gravity, well, gravity is the stubborn holdout, the one force we still haven't fully incorporated into quantum field theory. But the hypothetical exchange particle is called the graviton. Here's the thing, though. By the 1950s and 1960s, physicists had made enormous progress on electromagnetism. A quantum field theory of electromagnetism, called quantum electrodynamics, or QED, had been developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, and it was staggeringly accurate. It could predict the magnetic properties of the electron to something like 10 decimal places, matching experiment perfectly. QED is sometimes called the most precise theory in all of science, and that's not hyperbole. It really is. But when physicists tried to build a similar theory for the weak nuclear force, they hit a wall. And this wall, this specific technical obstacle, is exactly where the Higgs story really begins. See, the weak force has some peculiar properties. It's incredibly short range. It only operates over distances smaller than an atomic nucleus. And it's, well, weak. Much weaker than electromagnetism or the strong force. Both of these properties, the short range and the weakness, pointed to something specific about the particles that carry the weak force. Remember how electromagnetism is carried by photons? Photons are massless. They have zero mass, and it turns out that's deeply connected to why electromagnetism has infinite range. It can reach across the entire universe. The weak force, by contrast, has a tiny range, and the theoretical framework strongly suggested that its carrier particles, the W and Z bosons, must be very heavy, massive in physics terms. And this is where the crisis hit, because there was a beautiful mathematical framework called gauge symmetry that seemed to underlie all the forces. Gauge symmetry is one of those deep structural principles that physicists find incredibly powerful. It essentially says that the laws of physics don't change when you make certain kinds of transformations, and from that requirement alone, you can derive the existence of force-carrying particles. It's remarkable. You start with an abstract symmetry principle, you turn the mathematical crank, and out pop photons, gluons, all of it. But gauge symmetry had a very strict requirement. The force-carrying particles it predicted had to be massless. Zero mass, no exceptions. And that was fine for photons. Photons really are massless. But for the W and Z bosons, they couldn't be massless. The whole theory of the weak force demanded they be heavy, very heavy as it turned out, about 80 to 90 times the mass of a proton. So you had this impossible situation. The mathematical framework that made everything elegant and consistent and predictive, gauge symmetry, insisted the particles had to be massless. But the physical reality of the weak force demanded they have mass. If you just shoved mass into the equations by hand, the theory broke. The math produced infinities again, nonsense answers, the same kind of catastrophe that had plagued earlier attempts. It was as if the universe was using a beautiful, symmetric blueprint, but had somehow broken its own rules. And this is where a small group of theorists, working mostly independently in the early 1960s, had an idea that would change everything. What if the symmetry wasn't actually broken? What if it was hidden? What if there was a way for the W and Z bosons to acquire mass, not by violating gauge symmetry, but through a completely new mechanism, one that preserved the symmetry in the underlying equations, but disguised it in the world we actually observe? The concept they reached for had a name that sounds almost paradoxical: spontaneous symmetry breaking. And to understand what that means, I want you to think about something simple. Imagine a ball sitting at the very top of a perfectly round hill. The hill is symmetric. It looks the same in every direction. The ball at the top is in a symmetric position, but that position is unstable. The slightest breeze, the tiniest vibration, and the ball rolls down. It has to pick a direction. And once it does, the symmetry is broken, not because the hill changed shape, but because the ball chose a particular spot at the bottom. The underlying hill is still perfectly symmetric, but the ball's actual position isn't. The symmetry is hidden, not destroyed. Now, that's a simple analogy, and the real physics is more abstract, but the core idea is exactly right. What if there were a field, a new kind of field, filling all of space, that was like that hill? What if the equations governing this field were perfectly symmetric, but the field's actual state, its lowest energy configuration, broke that symmetry? And what if, in doing so, it gave mass to the W and Z bosons without ruining the beautiful mathematics of gauge theory? This was the insight, and several people arrived at versions of it around the same time, in that fertile, restless period of the early 1960s, when particle physics was bursting with new ideas, and new particles were being discovered in accelerators almost faster than theorists could name them. The story of who exactly deserves credit is complicated, and honestly, a little contentious. And we'll get into that, because it involves some fascinating characters: a shy British physicist working alone in Edinburgh, a group of theorists in Brussels, and an American whose contribution was overlooked for years. But before we get to the people, I want to make sure you have a feel for why this mattered so much. Because the idea wasn't just a clever trick to fix one equation. It was a new piece of the universe, a field that had never been detected, that nobody had ever seen direct evidence for, but that, if it existed, would explain something absolutely fundamental about reality. It would explain why particles have mass at all, why the universe has substance, why you, lying there right now, have weight. And the particle associated with that field, the quantum excitation of it, the ripple you'd get if you disturbed it with enough energy, that particle would come to be called the Higgs boson. But in 1964, when the first papers were being written, nobody called it that yet. Nobody knew if it was real. Nobody knew if it could ever be found. And the story of how we got from a handful of speculative equations scribbled on paper in Edinburgh and Brussels to a confirmed discovery announced to the world on the 4th of July 2012 in a packed auditorium in Geneva. That story spans half a century, involves thousands of people, costs billions of dollars, and requires building a machine so large and so precise that it stretches beneath the countryside of 2 countries. We'll get to that machine. But right now, let's talk about the people. So, the shy British physicist, his name is Peter Higgs, and by the early 1960s, he was a relatively unknown theoretical physicist at the University of Edinburgh. Not a nobody exactly. He'd done solid work in quantum field theory, but he wasn't one of the big names. He wasn't at Princeton or Cambridge or any of the powerhouse institutions where the most celebrated work in particle physics was happening. He was in Edinburgh, which was a fine university, but not exactly the center of the theoretical physics world. And Higgs was, by all accounts, a quiet man. Not the type to elbow his way into the spotlight. He liked to think deeply, work carefully, and he had a habit of going on long walks in the Scottish Highlands when he was stuck on a problem. There's something lovely about that image, right? A man wandering through the hills above Edinburgh, turning over equations in his head, trying to figure out why particles have mass. Now, the problem Higgs was wrestling with, and he wasn't the only one, was exactly the crisis we talked about. You've got gauge symmetry, this beautiful mathematical framework that describes how forces work, and it demands that the particles carrying those forces be massless. That works perfectly for photons, which are indeed massless, and for gluons. But it falls apart for the weak force because the W and Z bosons clearly have mass, a lot of mass. They're roughly 80 to 90 times heavier than a proton. So something is wrong, or rather, something is missing. The symmetry has to be there. The math is too elegant and too predictive to throw away. But it also has to be broken somehow, in a way that lets certain particles acquire mass while keeping the underlying equations intact. And this is where the concept of spontaneous symmetry breaking comes in, which we touched on with the idea of a ball sitting on top of a perfectly symmetric hill. The laws governing the ball are symmetric. There's no preferred direction, but the ball has to roll somewhere, and once it does, the symmetry is broken. The ground state, the resting state, the state where things actually end up, doesn't look symmetric anymore, even though the rules that got you there are perfectly symmetric. That idea had been floating around in physics for a while, particularly in condensed matter physics, the physics of solids and liquids and materials. In fact, there's a direct ancestor of the Higgs mechanism hiding in the theory of superconductivity. Let me take a small detour here because this connection is genuinely beautiful and it will help everything else make more sense. In 1957, three physicists, John Bardeen, Leon Cooper, and Robert Schrieffer, published a theory explaining how superconductivity works. Superconductivity is this remarkable phenomenon where certain materials, when cooled to extremely low temperatures, lose all electrical resistance. Current flows through them forever, with zero loss. Their theory, called BCS theory, showed that at low temperatures, electrons in a superconductor pair up into what are called Cooper pairs, and these pairs form a kind of collective quantum state, a condensate that fills the material. And here's the crucial part. Inside a superconductor, photons effectively become massive. Electromagnetic fields can't penetrate very far into a superconductor. That's the Meissner effect, if you've ever heard of it. And mathematically, the reason is that the photon, which is normally massless, acquires an effective mass inside the superconducting material because of its interaction with that condensate. Think about what that means. You have a normally massless particle, the photon, and by placing it inside a medium with a particular kind of order, a particular kind of broken symmetry, it starts behaving as if it has mass. The underlying laws of electromagnetism haven't changed. The symmetry is still there in the equations, but the environment, the ground state, the condensate filling the material, that breaks the symmetry and gives the photon mass. A Japanese-American physicist named Yoichiro Nambu was one of the first to see that this kind of thinking could be applied to particle physics more broadly. Nambu was brilliant. He'd eventually win the Nobel Prize in 2008. And in the early 1960s, he was exploring how spontaneous symmetry breaking could work in the vacuum of space itself, not inside a superconductor, but everywhere. The vacuum wouldn't be empty. It would be filled with some kind of field, some kind of condensate, and particles moving through it would interact with that condensate and acquire mass. It was a stunning idea. But Nambu's work ran into a technical problem, a problem that had been identified by a British physicist named Geoffrey Goldstone. Goldstone showed, and this was later proved more rigorously in collaboration with Abdus Salam and Steven Weinberg, that whenever you spontaneously break a continuous symmetry, you inevitably produce massless particles called Goldstone bosons. And nobody had ever seen these particles. They didn't seem to exist. So if you tried to use spontaneous symmetry breaking to give mass to the W and Z bosons, you'd solve one problem, but create another. You'd predict a bunch of massless particles that aren't there. This was called the Goldstone theorem, and in the early 60s it looked like a fatal objection. It seemed to kill the whole approach. And this is where 1964 comes in, and where the story gets both exciting and a little tangled. Because in that single year, 3 groups of physicists independently found a way around the Goldstone theorem. They showed that when you combine spontaneous symmetry breaking with a gauge symmetry, specifically a local gauge symmetry, the kind that gives rise to force-carrying particles, something magical happens. The Goldstone bosons don't appear as independent particles. Instead, they get absorbed by the gauge bosons, and in the process, those gauge bosons acquire mass. The massless particles that Goldstone's theorem predicted aren't gone. They're eaten, in the physicist's own colorful language. They become the extra degree of freedom that a massive particle has compared to a massless one. A massless particle, like a photon, can only spin in 2 directions relative to its motion. A massive particle can spin in 3. That third mode of spinning, that extra polarization, that's the Goldstone boson, absorbed and hidden inside the now massive gauge boson. It's one of the most elegant pieces of theoretical physics ever constructed, and 3 groups found it essentially simultaneously. The first paper was by François Englert and Robert Brut, working at the Université Libre de Bruxelles. Englert was Belgian. Brut was American-born, but had moved to Brussels. They submitted their paper in June of 1964, and it laid out the basic mechanism clearly and concisely. They showed how spontaneous symmetry breaking in a gauge theory could give mass to gauge bosons without producing unwanted Goldstone bosons. Their paper was short, just a couple of pages, and it was correct. A few weeks later, Peter Higgs submitted his own paper. Actually, he submitted 2 papers. The first was a short note pointing out that Goldstone's theorem had a loophole when applied to gauge theories. The second paper, the famous one, worked out a specific model. And here's the thing that makes Higgs's contribution distinctive. In that second paper, he explicitly pointed out that the theory predicted a new massive particle, a scalar boson, a leftover from the symmetry breaking mechanism. Englert and Brut had described the mechanism, but they hadn't drawn attention to this particle. Higgs did. He wrote it down, noted its properties, and essentially said, if this mechanism is real, this particle should exist. That particle is what we now call the Higgs boson. And there's a wonderful story about that second paper. Higgs initially submitted it to the journal Physics Letters, which was based at CERN in Geneva, and they rejected it. The editor didn't think it was significant enough. Can you imagine? The paper predicting one of the most important particles in physics, rejected. Higgs was discouraged, but he revised the paper, added some more discussion, including more emphasis on the predicted massive boson, and sent it instead to Physical Review Letters in the United States, where it was accepted and published in October 1964. Years later, Higgs would say that the rejection actually improved the paper because it pushed him to be more explicit about the physical consequences, including the existence of that new particle. Sometimes, a rejection is a gift. Now, the third group. And this is the part of the story that carries a real sense of injustice, at least to some people. Gerald Guralnick, Carl Hagen, and Tom Kibble, working at Imperial College London, independently arrived at the same mechanism. Their paper was submitted slightly later than the other two, in October 1964, and it's a thorough, careful piece of work. In some ways, it's the most complete of the three, because they explicitly addressed the Goldstone theorem and showed precisely how and why it was evaded in this context. But because it came last, and because the Nobel Prize can only be shared among three people, Guralnick, Hagen, and Kibble were left out when the prize was finally awarded in 2013. Guralnick in particular felt the sting of this. He passed away in 2014, and friends said the omission weighed on him. The Nobel Committee acknowledged all three papers in their scientific background document, but the prize itself went to Englert and Higgs. Brout had died in 2011, so he couldn't share it. Kibble, who was widely respected and had gone on to do enormously influential work in cosmology and phase transitions, also received no Nobel for this. He died in 2016. It's worth sitting with that for a moment, because it tells you something about how science actually works versus how we like to tell the story. We want a clean narrative, one person, one idea, one breakthrough. But reality is messier. Three groups, working independently, within weeks of each other, all seeing the same deep truth about nature. That's not a coincidence. It means the field was ready, the tools were in place, the problem was ripe, and multiple brilliant minds converged on the answer almost simultaneously. It happens more often than you'd think in the history of science, but having the theoretical mechanism on paper was only the beginning. Because here's the uncomfortable truth that hung over particle physics for the next several decades. Nobody could test it. The theory predicted that the W and Z bosons should exist and should have specific masses, and it predicted that a new scalar boson, the Higgs boson, should exist too. But actually finding these particles required energies that no accelerator on Earth could reach in 1964. Not even close. So the theory sat there. Beautiful, elegant, potentially the key to understanding why anything in the universe has mass, and completely unverified. Theoretical physics is full of beautiful ideas that turn out to be wrong. Without experimental confirmation, the Higgs mechanism was just a possibility, very good possibility, one that fit naturally into the emerging framework of particle physics, but still just a possibility. And what happened next is that a handful of theorists took this mechanism and used it to build something much larger, something that would become one of the most successful scientific theories in human history. In 1967, Steven Weinberg, working at MIT, published a paper that unified the electromagnetic force and the weak nuclear force into a single framework, using the Higgs mechanism to give mass to the W and Z bosons while keeping the photon massless. Abdus Salam, working independently at Imperial College London, arrived at essentially the same theory around the same time. Their model, which also built on earlier work by Sheldon Glashow, became known as the electroweak theory, and it was a masterpiece of theoretical physics, But here's the thing. When Weinberg published that paper in 1967, almost nobody noticed. I mean that literally. His paper, which would eventually become one of the most cited papers in the history of physics, received almost no citations for the first few years. People read it, shrugged, and moved on. And you can understand why, in a way. The theory was mathematically elegant, sure, but it made predictions about particles nobody had ever seen, at energies nobody could reach, and it relied on a mechanism, the Higgs mechanism, that was itself unproven. Worse, there was a serious technical question hanging over the whole thing. Was the theory even mathematically consistent? Could you actually use it to calculate things without getting nonsensical infinities popping up everywhere? This is a problem called renormalizability, and it's worth taking a moment to understand why it mattered so much. In quantum field theory, when you try to calculate the probability of something happening, say two particles scattering off each other, you don't just get one clean answer. You get an infinite series of corrections, each one representing a more complicated way the interaction could play out. And some of those corrections give you infinite results, not large numbers. Literally, infinity. Now, in QED, quantum electrodynamics, the theory of the electromagnetic force, Feynman, Schwinger, and Tomonaga had figured out a procedure called renormalization that could tame those infinities. You could absorb them into the definitions of quantities like mass and charge, and what was left over gave you finite, meaningful, astonishingly precise predictions. That's why QED worked so beautifully. But not every theory can be renormalized. Some theories, when you try to do the same trick, just keep spawning new infinities that you can't absorb. They're mathematically sick. And nobody was sure whether the electroweak theory, this new unified framework that Weinberg and Salam had built using the Higgs mechanism, was renormalizable or not. If it wasn't, the whole thing was just a pretty toy. Interesting but useless for making real predictions. This is where a young Dutch graduate student changed everything. His name was Gerard 't Hooft, and in 1971, working under his advisor Martinus Veltman at Utrecht University, he proved that the electroweak theory was indeed renormalizable. The theory was mathematically consistent. You could use it to calculate things, real things, and get finite answers. And suddenly, people paid attention. Weinberg's ignored paper from 1967 started getting cited like crazy. The electroweak theory went from an interesting speculation to a serious, calculable framework that made specific, testable predictions. Hooft was in his mid-20s when he did this. Veltman had been working on the problem for years, developing computational tools and techniques, and 't Hooft, his student, walked in and cracked the final piece. The two of them shared the Nobel Prize in 1999 for this work, and it's one of those beautiful stories where the advisor's years of groundwork and the student's flash of brilliance came together at exactly the right moment. So by the early 1970s, the electroweak theory was on solid mathematical footing. It predicted the existence of the W+ boson, the W- boson, and the Z boson, three massive particles that carried the weak force, along with the massless photon carrying the electromagnetic force. All four emerging from the same underlying symmetry, with the Higgs mechanism doing the work of breaking that symmetry and giving mass to the W and Z, while leaving the photon untouched. The theory also predicted the specific properties these particles should have, their masses, their interaction strengths, the precise ways they should decay. And it predicted the Higgs boson itself, a leftover ripple in the Higgs field, a particle that nobody had ever seen. Now here's what's interesting about the order of confirmation. You might think physicists went straight for the Higgs boson, since that was the linchpin of the whole mechanism. But they didn't. They couldn't. The Higgs boson was predicted to be heavy. Exactly how heavy, the theory couldn't say precisely, which was its own problem. But the W and Z bosons had predicted masses that were within reach of the next generation of particle accelerators, so the hunt focused there first. Find the W and Z, confirm the electroweak theory, and then worry about the Higgs. But before the W and Z were found directly, something else happened that gave physicists enormous confidence in the theory. In 1973, a collaboration at CERN using a massive bubble chamber called Gargamel. And I love that name. It's from Rabelais, the grandmother of Gargantua. They discovered something called neutral currents. Let me explain why this mattered. The weak force, as people understood it, always involved the exchange of charged particles. A neutron would emit a W- boson and turn into a proton, for example. The electric charge changed. That was the hallmark of the weak interaction. But the electroweak theory predicted that the Z boson, being electrically neutral, should mediate a new kind of weak interaction where no charge was exchanged. A neutrino could bounce off another particle and remain a neutrino. No charge transfer, no transformation, just a neutral current interaction. And that's exactly what the Gargamel team found. They saw neutrinos interacting with matter without changing into charged particles. It was subtle. It was hard to confirm. There were months of agonizing over whether the results were real or just background noise, but it held up. Neutral currents were real, and the electroweak theory had predicted them. Think about what that meant. A theory built on the Higgs mechanism, using spontaneous symmetry breaking to unify two forces, had just made a prediction about something nobody had ever observed before, and the prediction turned out to be correct. That's the gold standard in physics. Not just explaining what you already know, but telling you something new that you can go out and check. And it checked out. But the real showstopper came a decade later. In 1983, at CERN, a team led by Carlo Rubbia discovered the W and Z bosons directly. And this is a story worth lingering on because it involved not just brilliant physics, but a kind of relentless, almost aggressive ambition that reshaped what a particle physics experiment could be. Carlo Rubbia is one of those larger-than-life figures in physics. Italian-born, intense, demanding, the kind of person who would fly between continents multiple times a week to keep his various projects running. He had an idea in the late 1970s. Instead of building an entirely new accelerator to reach the energies needed to produce W and Z bosons, you could convert CERN's existing superproton synchrotron, the SPS, into a proton-antiproton collider. Normally, the SPS accelerated protons and smashed them into a fixed target. But if you could send protons one way and antiprotons the other way, head-on, you'd get much more energy out of each collision. The problem was antiprotons. They're antimatter. You can't just scoop them up somewhere. You have to create them, and when you do, they come out moving in all different directions with all different speeds. They're messy. To make a usable beam, you needed to somehow cool them down, corral them, tame them into a tight, focused beam that could circulate in the accelerator. And this is where Simon van der Meer comes in. Van der Meer, a Dutch engineer at CERN, had invented a technique called stochastic cooling. The basic idea is beautifully clever. You measure the average position of the antiprotons as they circulate, and then you send a correction signal across the ring, taking a shortcut through the diameter while the particles go the long way around the circumference, and that signal nudges the particles closer together. You're essentially sending a message to the other side of the ring saying, "They're drifting too far left, push them right," and the signal arrives just in time to do the pushing. It's like herding cats, except the cats are moving at nearly the speed of light, and you're using electronic whispers to nudge them into line. It worked. Rubbia's drive and Vandermeer's engineering made it possible to accumulate enough antiprotons to create a usable beam, and in January 1983, the UA-1 experiment, one of two massive detectors built around the collision points, announced the discovery of the W boson. The Z boson followed a few months later. The masses matched the predictions of the electroweak theory almost exactly. The W bosons came in at about 80 giga-electron volts, 80 times the mass of a proton, and the Z at about 91 giga-electron volts. Rubbia and Vandermeer shared the Nobel Prize in 1984, just 1 year after the discovery, which gives you a sense of how significant the physics community considered this result. And now the electroweak theory was confirmed. The unification of electromagnetism and the weak force was real. The Higgs mechanism worked. At least, it worked in the sense that the theory built on top of it made correct predictions. The W and Z bosons had the masses the theory said they should have. Neutral currents existed. Everything fit. But there was still this enormous loose end. The Higgs boson itself. The actual particle, the quantum of the Higgs field, the ripple in the medium that was supposedly responsible for giving everything mass, had never been seen. And here's the frustrating part. The electroweak theory told you almost everything about the Higgs boson, except the one thing you needed most. It told you how the Higgs should interact with other particles. It told you how it should be produced, how it should decay, what its spin should be. But it did not tell you its mass. The mass of the Higgs boson was a free parameter in the theory. It could be almost anything. Well, not anything. There were theoretical arguments that constrained it to a range, roughly between about 100 and 1,000 giga-electron volts. But that's an enormous window when you're trying to design an experiment to find it. Different masses mean different production rates, different decay patterns, different experimental signatures. Looking for the Higgs without knowing its mass was like searching for someone in a city, when all you know is that they're somewhere between the waterfront and the suburbs. So began what would turn into the longest, most expensive, most technically demanding search in the history of physics. And the machine that would ultimately end that search, the Large Hadron Collider, was already being dreamed about in the 1980s, even as the W and Z discoveries were still fresh. But dreaming about it and actually building it were two very different things, separated by decades of politics, engineering challenges, budget crises, and at least one catastrophic setback that nearly killed the whole enterprise. Because before the LHC, there was another machine, an American machine, that was supposed to find the Higgs first. It was called the Superconducting Supercollider, and what happened to it is one of the most painful stories in the history of American science. The Superconducting Supercollider, or SSC, was going to be the biggest, most powerful particle accelerator ever built. We're talking about a ring of superconducting magnets stretching 54 miles around. That's more than 3 times the circumference of the LHC that eventually got built in Geneva. It would have collided protons at 40 trillion electron volts, roughly 6 times the energy the LHC would achieve decades later. This thing was going to be a monster, and it was going to be built in Waxahachie, Texas, about 30 miles south of Dallas, in a tunnel bored through the chalky Austin limestone beneath the Texas prairie. The project got its start in the early 1980s, when American physicists realized that finding the Higgs boson and probing whatever physics lay beyond the standard model was going to require energies far beyond what existing accelerators could reach. In 1987, President Reagan endorsed the project. Congress authorized it. Texas won the site competition, partly by offering $1 billion in state support, and for a few years, everything seemed to be moving forward. They started digging the tunnel. They built surface facilities. They hired thousands of engineers and physicists. By the early 1990s, about 14 miles of tunnel had been excavated. Real, physical tunnel, bored through real rock with real money. And then it all fell apart. The cost estimates kept climbing. The original price tag was around $4.5 billion, which was already enormous. But as the project progressed, that number crept up toward $8 billion, then past 10, then toward $12 billion. Every time the estimate went up, congressional support eroded a little more. And there were other factors too. The Cold War had ended, which removed some of the competitive pressure that had historically driven big science funding in the United States. The space station program was competing for the same pot of money. And honestly, the physics community didn't always do itself favors in how it communicated why this mattered. When a senator asks you what the superconducting super collider will find, and you say, "We're looking for the Higgs boson," and the senator says, "What's that?" and you try to explain spontaneous symmetry breaking and the mechanism by which gauge bosons acquire mass, well, you can see the problem. The connection between this deeply abstract physics and anything a taxpayer might care about was genuinely hard to articulate. In October 1993, Congress voted to cancel the SSC. Just like that, 14 miles of tunnel already dug, $2 billion already spent, and they pulled the plug. The tunnel sits there to this day, actually, or what's left of it. Parts of it have been repurposed. Parts have flooded. There's something almost archaeological about it, this underground monument to a machine that never was. The cancellation of the SSC was devastating for American high-energy physics. It essentially handed the future of particle physics to Europe, to CERN, which had been quietly developing its own plans for a Large Hadron Collider. And here's where the story shifts across the Atlantic, to a place you might not expect to find the most complex machine ever built by human beings, buried 100 meters beneath the French-Swiss border, in the same tunnel that had been dug back in the 1980s for an earlier accelerator called the Large Electron-Positron Collider, or LEP. The LEP tunnel was already there, 27 kilometers around, roughly 17 miles, straddling the border between France and Switzerland near Geneva. LEP had done beautiful physics throughout the late 1980s and 1990s, precision measurements of the Z boson that confirmed the electroweak theory with extraordinary accuracy. But LEP was an electron-positron machine, and electrons are light particles, which means they lose enormous amounts of energy to synchrotron radiation when you bend them around a curve. There's a fundamental limit to how much energy you can reach with electrons in a circular machine. Protons, being about 2,000 times heavier, lose far less energy to radiation at the same speed. So, the plan was to retire LEP and install a proton-proton collider in the same tunnel, the Large Hadron Collider. Now, you might think that having an existing tunnel would make things easy. And it helped, certainly. Tunneling is expensive, and the civil engineering was largely done. But fitting the LHC into the LEP tunnel was actually a massive constraint. The tunnel's circumference was fixed, which meant the energy you could reach depended entirely on how strong you could make the bending magnets. And this is where the engineering becomes genuinely extraordinary. Think about what a circular collider does. You have particles flying around a ring at nearly the speed of light, and you need magnets to bend their path into that circle. The faster the particles go, the more energy they carry. The stronger the magnets need to be to keep them on track. It's the same principle as driving a car around a curve. The faster you go, the more force you need to keep you from flying off the road. For the LHC to reach its design energy of 7 trillion electron volts per beam, 14 TeV in total when two beams collide head-on, you need magnets producing fields of about 8.3 Tesla. For reference, a typical refrigerator magnet produces maybe 0.005 Tesla. An MRI machine, which already uses superconducting magnets, produces 1.5 to 3 Tesla. The LHC magnets needed to be roughly 3 to 5 times stronger than an MRI, and you needed over 1,200 of them, each one 15 meters long, arranged in a precise arc around the entire 27-kilometer ring. These magnets are superconducting, which means their coils are made of special alloys, niobium titanium in this case, that lose all electrical resistance when cooled below a critical temperature. For niobium titanium, that temperature is about 10 Kelvin, or minus 263 degrees Celsius. But the LHC magnets actually operate at 1.9 Kelvin, colder than outer space, colder than the cosmic microwave background radiation that fills the universe. They use superfluid helium as a coolant, which has this almost magical property of having essentially zero viscosity, allowing it to creep into every tiny space and cool the magnets with incredible uniformity. The LHC's cryogenic system is the largest in the world. It uses about 96 metric tons of superfluid helium. Cooling the entire machine down from room temperature takes weeks. And here's a detail that I find just wonderful in its engineering cleverness. Because the LHC collides two beams of protons traveling in opposite directions, you need two beam pipes, each with its own set of bending magnets, one bending clockwise, one bending counterclockwise. In a larger tunnel, you might just put two separate rings of magnets side by side. But the LEP tunnel wasn't wide enough for that. So the LHC engineers designed a twin-bore magnet, a single magnet structure containing two beam pipes with magnetic fields pointing in opposite directions, all sharing the same cryostat, the same cooling system, the same mechanical structure. It's called the two-in-one design, and it was one of the key innovations that made the LHC possible in the existing tunnel. Thousands of these magnets, each one a precision instrument operating at nearly absolute zero, each one aligned to within fractions of a millimeter over a distance of 15 meters. The construction took about a decade. The LHC was approved by CERN's Governing Council in 1994, just a year after the SSC was canceled, which is a timing that feels almost poetic. Components were manufactured in factories across Europe and around the world, shipped to CERN, lowered down shafts into the tunnel, and assembled underground. The project involved contributions from over 10,000 scientists and engineers from more than 100 countries. Its total cost was roughly $9 billion, which sounds like a lot until you remember that the SSC was projected to cost more than that and would have been built from scratch. By September 2008, the LHC was ready for its first test. Proton beams were successfully circulated around the ring on September 10th, and the world watched with a mixture of excitement and, let's be honest, a little bit of anxiety, because there had been some genuinely silly but widely publicized fears that the collider might create a black hole that would swallow the Earth. It didn't, of course. The energy in LHC collisions, while enormous by particle physics standards, is roughly equivalent to the kinetic energy of a mosquito in flight. cosmic rays hitting the upper atmosphere produce collisions of similar or greater energy billions of times a day. And the Earth is still here. But then, just 9 days later, on September 19, 2008, disaster struck. A faulty electrical connection between two of the superconducting magnets failed, causing an electrical arc that punctured the helium containment. Superfluid helium, 6 tons of it, vaporized and expanded explosively. The pressure wave damaged over 50 magnets along a stretch of the tunnel. Some magnets were ripped from their mountings. The tunnel was contaminated with soot from the electrical arc. It was a catastrophe. Not a human catastrophe, thankfully. No one was in that section of the tunnel. But an engineering catastrophe that would take over a year and roughly $40 million to repair. And this is worth pausing on for a moment, because it tells you something important about the nature of engineering at this scale. The LHC has roughly 10,000 electrical interconnections between its superconducting magnets. Each one carries enormous currents, up to 13,000 amperes. Each one must maintain superconductivity, meaning zero resistance, meaning perfect contact, at 1.9 Kelvin. If even one of those connections has a tiny flaw, a spot where the resistance is slightly higher than zero, then when you run 13,000 amps through it, that spot heats up. And when a superconductor heats above its critical temperature, it suddenly stops being superconducting. The resistance goes from zero to something, and all that electrical energy has to go somewhere. It's called a quench, and it can be violent. The September 2008 incident was essentially a quench triggered by a bad solder joint. One bad joint out of 10,000, and it shut the machine down for 14 months. They fixed it. They added new safety systems, additional quench protection, pressure relief valves, an early warning system to detect tiny resistance anomalies before they could cascade. And in November 2009, the LHC circulated beams again. By March 2010, it was colliding protons at 3.5 TeV per beam, 7 TeV total, half its design energy, but already the highest collision energy ever achieved. And the hunt for the Higgs began in earnest. Now, finding the Higgs boson at the LHC is nothing like finding a ball in a field. You can't just look for it. The Higgs boson, if it exists, would be produced in only a tiny fraction of the collisions, and it would decay almost instantly in about a zeptosecond, which is a trillionth of a billionth of a second. You never see the Higgs itself. You see what it decays into. And the problem is that the things it decays into, pairs of photons, pairs of Z bosons, pairs of W bosons, pairs of bottom quarks, are also produced by plenty of other processes that have nothing to do with the Higgs. These other processes are called background, and they are overwhelming. For every collision that might produce a Higgs boson, there are billions of collisions producing ordinary, well-understood particles that look superficially similar. So the game is statistical. You collide protons billions of times. You record what comes out. You calculate, using the standard model, exactly how many events of each type you'd expect to see if there were no Higgs boson. Then you look at your actual data and ask, is there a little bump, a little excess at some particular mass above what the background predicts? And if there is, you ask, could this bump be a statistical fluke? Because when you're looking at millions of events, random fluctuations happen all the time. A bump that looks exciting one week might disappear the next as you collect more data. Particle physicists have a very strict standard for claiming a discovery. They require what's called a 5 sigma result, meaning the probability that the observed bump is a random fluctuation of the background must be less than about 1 in 3.5 million. That's an extraordinarily high bar. Most sciences would be thrilled with 3 sigma. particle physics demands 5, because the history of the field is littered with 3 sigma bumps that turned out to be nothing. The 2 main detectors at the LHC tasked with finding the Higgs were ATLAS and CMS, 2 enormous independent experiments built around 2 of the 4 collision points along the ring. And when I say enormous, I mean it. The ATLAS detector is 46 meters long, 25 meters in diameter, and weighs 7,000 metric tons. CMS is smaller in length but denser, about 15 meters long, 15 meters in diameter, and 14,000 metric tons, making it one of the densest objects humans have ever constructed. Each one is essentially a giant camera designed to photograph the debris from proton collisions, with layers of different detector technologies, tracking chambers to follow charged particles, calorimeters to measure energy, muon detectors on the outside, all wrapped in powerful magnetic fields to bend particle trajectories so you can measure their momenta. Each collision produces hundreds of particles flying outward in all directions, and the detectors must reconstruct what happened in the collision from this spray of debris, 40 million times per second. The data rates are staggering, even after aggressive filtering, keeping only the most interesting-looking collisions and discarding the rest in real time. The experiments each record petabytes of data per year. Through 2010 and 2011, the data accumulated. The range of possible Higgs masses was being narrowed, squeezed from both sides. The LEP Collider, before it was decommissioned, had already established that the Higgs must be heavier than about 114 gigaelectron volts. If it were lighter, LEP would have seen it. The Tevatron at Fermilab, the old American collider that had been running since the 1980s, was also searching and had excluded some mass ranges. By late 2011, the LHC experiments had narrowed the window further. If the Higgs existed, it was hiding somewhere between about 115 and 130 gigaelectron volts. The net was closing, and then, in December 2011, both ATLAS and CMS independently reported seeing something, tantalizing hints, little excesses in their data, right around 125 gigaelectron volts. Not statistically significant enough to claim a discovery. Maybe 3 sigma each. Exciting, but not conclusive. The kind of result that makes physicists lie awake at night wondering if they're about to find what they've been looking for, or if the universe is playing a cruel statistical joke. The collaborations went into overdrive, analyzing every last bit of 2011 data, refining their techniques, preparing for the flood of new data that would come when the LHC started up again in the spring of 2012. And what happened over the next 6 months is one of the most intense and focused periods of scientific effort in modern history. Because those physicists knew they were close. They could feel it, and the pressure was extraordinary. When the LHC fired up again in April 2012, it came back with a boost. The collision energy was raised from 7 TeV total to 8 TeV, 4 TeV per beam instead of 3.5. That might sound like a modest increase, maybe 15%, but in particle physics, even a small bump in energy can make a meaningful difference. Higher energy means the collisions are more violent, which means heavier particles can be produced more often. And crucially, the machine was also delivering more collisions per second than before. The luminosity, that's the term physicists use for how many collisions you're packing into a given time, was climbing. More collisions means more chances to produce a Higgs boson, and more chances means the statistical signal, if it's real, grows faster. Now here's something worth pausing on for a moment, because it's easy to gloss over. The Higgs boson, if it has a mass around 125 gigaelectron volts, is actually produced pretty rarely even at the LHC. Most proton-proton collisions produce mundane stuff, jets of ordinary particles, well-understood processes that physicists call background. For every billion collisions, maybe one produces a Higgs boson, and then the Higgs doesn't stick around. It decays almost immediately, in something like a trillionth of a second. You never see the Higgs itself. You only see what it decays into. So the whole game is looking at the decay products, pairs of photons, pairs of Z bosons, pairs of W bosons, pairs of bottom quarks, pairs of tau leptons, and asking whether there are slightly more events at a particular energy than you'd expect from background processes alone. Think about what that means practically. You're sifting through billions and billions of collisions, looking for a tiny statistical bump sitting on top of a mountain of noise. It's like trying to hear someone whispering your name across a stadium during a football game. Except you can't just listen harder. You have to record everything, analyze it all, model the background with extraordinary precision, and then see if there's a little excess left over that can't be explained by anything else. The two big experiments, ATLAS and CMS, were each doing this independently. And that independence is really important. These are separate detectors, built by separate teams, using different technologies, different software, different analysis strategies. If both of them see the same bump at the same mass, it's very hard to argue it's a fluke or a systematic error. The probability that both experiments would independently produce a false signal at the same mass is vanishingly small. Through April, May, and June of 2012, the data poured in. The LHC was performing beautifully, better than anyone had dared hope, actually. The machine was delivering collisions at a rate that exceeded its design specifications for that energy. And inside the two big collaborations, hundreds of physicists were working around the clock analyzing the incoming data in near real time. There were subgroups dedicated to each decay channel, the diphoton team, the 4-lepton team, the WW team, and each group was watching their signal grow, week by week. Here's the thing about those decay channels that makes this story even more interesting. Not all of them are equally clean. The cleanest, most beautiful channel for finding a Higgs at 125 giga-electron-volts is the decay into two photons. A Higgs boson can decay into a pair of high-energy photons, and photons are easy to measure precisely. The electromagnetic calorimeters in ATLAS and CMS can measure photon energies with exquisite accuracy. So when you plot the combined energy of photon pairs from all your collisions, you see a smooth falling background curve. And if there's a Higgs, you see a little bump, a narrow peak sitting on top of that curve, right at the Higgs mass. It's visually striking when you see the plot. This little bump at 125 giga-electron-volts, poking up above the smooth background like a small hill on a plane. The other golden channel is the decay into two Z bosons, where each Z then decays into a pair of leptons, electrons or muons. So you end up looking for events with 4 leptons, 4 charged particles with very specific properties. This channel has an incredibly low background. There's almost nothing in the standard model that produces 4 leptons with the right characteristics to fake a Higgs signal. So even though the Higgs rarely decays this way, maybe 1 in every few thousand Higgs bosons takes this path, the events that do show up are spectacularly clean. Each 4-lepton event at the right mass is like a little gem. You don't need thousands of them. Even a handful, clustering at the same mass, is powerfully suggestive. By mid-June, the physicists could see it. Both channels in both experiments were showing excesses at the same mass. The bump was growing. The whisper was getting louder. But they hadn't crossed the magic threshold yet. 5 sigma. That gold standard of particle physics that means there's less than a 1 in 3.5 million chance the signal is a random fluctuation. They were close, though, tantalizingly close. And now the story gets a human dimension that I love. CERN had already scheduled a major international conference, the International Conference on High Energy Physics, ICHEP, for July 4th through 11th in Melbourne, Australia. This is one of the biggest gatherings in particle physics, happens every 2 years. The 2012 edition was set to open on July 4th. And the CERN leadership made a decision. They would hold a special seminar at CERN on the morning of July 4th, timed so that the results could be presented simultaneously in Geneva and broadcast to the conference in Melbourne. The date was set. The world was watching. But here's the pressure this created. The experimentalists had a hard deadline. They needed to finish their analyses, review them internally, check every systematic uncertainty, and have final results ready by early July. This meant the last 2 weeks of June were absolutely frenetic. People were sleeping in their offices. Graduate students were running final cross-checks at 3 a.m. The internal review committees within Atlas and CMS, because these collaborations have rigorous internal review processes, you don't just publish whatever one person finds. We're scrutinizing every detail. Are the background models correct? Have you accounted for every source of systematic error? Is there any way this could be an artifact of the detector, a calibration issue, a software bug? And through all of this, the two experiments weren't supposed to be talking to each other about their results. The independence had to be maintained. But of course, these are human beings working in adjacent buildings. There were rumors, glances in the cafeteria. A colleague from Atlas might notice that their friends in CMS seemed unusually excited or unusually stressed and draw their own conclusions. The tension was incredible. Peter Higgs was invited to attend the seminar. He was 83 years old. He'd proposed this mechanism in 1964, 48 years earlier. François Englert was invited too. These men had spent decades wondering whether the particle that bore their names would ever be found, whether the idea they'd had as young theorists would be confirmed by nature. Imagine carrying that question for almost half a century. The morning of July 4th, 2012, the main auditorium at CERN. It's not a huge room, maybe seats a few hundred people, was packed hours before the seminar was supposed to start. People had camped out overnight in the hallway to get seats. Graduate students, senior professors, Nobel laureates, all sitting on the floor, crammed into every available space. The seminar was webcast globally, and physicists at universities and labs around the world gathered in lecture halls to watch together. Joe Incandela presented the CMS results first. He's an American physicist, calm and methodical, and he walked through the analysis channel by channel. The diphoton bump, the 4 lepton events, the combined significance, 4.9 sigma, just barely below 5 sigma on its own, but with every channel pointing to the same mass, right around 125 to 126 giga-electron volts. Then, Fabiola Gianotti presented for Atlas. She's Italian, and she'd later become the Director General of CERN, the first woman to hold that position, actually. She walked through the Atlas results with similar care. Their diphoton channel alone was showing a strong excess. Their 4 lepton channel had a cluster of events right at 126 giga-electron volts. Combined significance, 5 sigma. The room erupted, 5 sigma. After 48 years, after billions of dollars, after the cancelled superconducting super collider, after the explosion and 14 months of repairs, after thousands of physicists from dozens of countries working for decades. 5 sigma. The Higgs boson, or at least a particle that looked exactly like it, had been found. The cameras caught Peter Higgs in the audience, wiping tears from his eyes. He later said he never expected to see this in his lifetime. François Englert was beaming. Rolf Dieter Hoyer, the CERN Director General at the time, stood up and said carefully, "I think we have it." And then, with a slight smile, "Do you agree?" The room erupted again. Now you might notice that Hoyer was being cautious with his words. He said, "I think we have it," not, "We've discovered the Higgs boson." And the official CERN press release was similarly careful, announcing the discovery of a new particle consistent with the Higgs boson. Why the hedging? Because finding a bump at 125 gigaelectronvolts is one thing. Confirming that this particle actually is the Higgs boson, that it has all the properties predicted by the theory, is another thing entirely. And that distinction matters a lot. Let me explain why. The Standard Model makes very specific predictions about how the Higgs boson should behave. It predicts not just that the particle exists and has some mass, but exactly how it should decay, and how often it should decay into each possible set of particles. A Higgs at 125 gigaelectronvolts should decay into pairs of bottom quarks most often, about 58% of the time. It should decay into pairs of W bosons about 21% of the time, into pairs of gluons about 9%, into pairs of tau leptons about 6%, into pairs of Z bosons about 2.5%, and into pairs of photons only about 0.2% of the time. But those photon decays are the easiest to spot cleanly, which is why they were so important for the discovery. So the question after July 4th wasn't just, is there a particle at 125 gigaelectronvolts? The question was, does this particle decay in exactly the ratios the Standard Model predicts? Because if it didn't, if, say, it decayed into photons way more often than expected, or never decayed into tau leptons when it should, that would mean it was something else. Something new and unexpected. Maybe a Higgs boson, but not the Standard Model Higgs boson. Maybe a Higgs from some more exotic theory, like supersymmetry, which predicts not one Higgs boson, but 5. And this is where the story shifts from the drama of discovery to something quieter, but in some ways even more profound, the painstaking work of measurement. Because after the champagne and the tears and the press conferences, the physicists went right back to work. They had a particle. Now they had to figure out exactly what it was. And the way you do that is you keep collecting data, keep measuring, keep checking every predicted property against what you actually observe. It's meticulous, unglamorous work. No more breathless countdowns, just careful, patient science. Through the rest of 2012, the LHC kept running, and the data kept accumulating. The collaborations began measuring the new particle's properties one by one. Its spin. The Standard Model Higgs should have spin 0, which is actually unusual. Most particles physicists deal with have spin 1/2 or spin 1. A spin 0 fundamental particle had never been observed before. The early measurements confirmed. Spin 0. Its parity, a quantum mechanical property related to how the particle behaves under mirror reflection, should be positive. The measurements were consistent with positive parity. Its coupling strengths to other particles, how strongly it interacts with W bosons versus Z bosons, versus top quarks versus bottom quarks versus tau leptons. these should follow a very specific pattern. The Higgs is supposed to couple to each particle in proportion to that particle's mass. Heavier particles should interact with the Higgs more strongly. This is the whole point of the Higgs mechanism, right? The reason particles have different masses is that they interact with the Higgs field with different strengths. So if you measure how often the new particle decays into various things, you should see this mass proportional pattern emerge. And slowly, over months and then years, that pattern did emerge. Every measurement came back consistent with the standard model prediction. Not exactly on the nose every time. There's always statistical uncertainty, always error bars, but always within the expected range. The particle at 125 gigaelectronvolts was behaving exactly like the textbook Higgs boson. By March 2013, CERN felt confident enough to drop the hedging. The new particle was officially identified as a Higgs boson. And in October 2013, Peter Higgs and François Englert were awarded the Nobel Prize in Physics. The committee noted that the prize was for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle. 49 years from theory to Nobel Prize. But here's what's fascinating and what a lot of people don't realize. The discovery of the Higgs boson wasn't the end of the story. In a very real sense, it was the beginning of a new one. Because while the Higgs completed the standard model, snapped the last piece into the puzzle, it also opened up a whole set of new questions that are, if anything, even more puzzling than the ones it answered. And some of those questions have to do with the Higgs mass itself, with that number, 125 gigaelectronvolts, and what it might be telling us about the deeper structure of reality itself. So let's talk about that number. 125 gigaelectronvolts. Why does it matter so much? On the surface, you might think, well, the Higgs had to have some mass, right? It turned out to be 125 gigaelectronvolts, which is roughly 133 times the mass of a proton. Fine, just a number. But in particle physics, numbers are never just numbers, they're clues. And this particular number sits in a very strange, very specific place. A place that has kept theoretical physicists up at night for over a decade now. To understand why, you need to know about something called the hierarchy problem. And don't let the name intimidate you. The core idea is actually pretty intuitive once you see it. Here's the thing. In quantum field theory, nothing is ever just itself. Every particle, every field, is constantly being buffeted by quantum fluctuations. Virtual particles popping in and out of existence, remember? We talked about that earlier, how the vacuum isn't really empty, how it's this seething, buzzing foam of activity. Well, those virtual particles don't just sit there minding their own business. They interact with real particles. They contribute to the properties of real particles. And one of the properties they contribute to is mass. So when you ask, what is the mass of the Higgs boson, the answer isn't just whatever the Higgs field's own parameters say it should be. You have to add in the contributions from every virtual particle that interacts with the Higgs, every quark, every lepton, every gauge boson. They all create little quantum loops that feed back into the Higgs mass. And here's where it gets really uncomfortable. Those contributions aren't small. In fact, if you just naively calculate them, if you add up all the quantum corrections from every particle up to the highest energy scales where we think our physics still applies, you get a number that's absolutely enormous. Not 125 gigaelectronvolts. Not even close. You get something closer to the Planck scale, which is about 10 to the 18th gigaelectron volts. That's a 1 followed by 18 zeros. Compared to 125, that's, well, it's like expecting a cup of water and getting an ocean. Think about what that means. The natural expectation, if you just follow the math of quantum field theory, is that the Higgs boson should be absurdly, incomprehensibly heavy. The fact that it's not, the fact that it's this relatively modest 125 gigaelectron volts, means that something is canceling out those enormous quantum corrections almost perfectly. Almost, but not quite. The corrections are huge and positive, and something else is huge and negative, and they cancel to leave this tiny residual of 125 gigaelectron volts. The degree of cancellation required is something like 1 part in 10 to the 34th. It's like two numbers, each 34 digits long, that just happen to be almost exactly equal, but with opposite signs, leaving a remainder that's tiny by comparison. Now, you might say, so what? Maybe that's just how nature is. Maybe the parameters of the universe just happen to be tuned that precisely. And technically, sure, that's possible. The standard model works perfectly well with those values plugged in. But it makes physicists deeply, profoundly uneasy. Because in the history of physics, whenever you've seen that kind of absurd fine-tuning, it's usually meant that you're missing something. There's a deeper mechanism at work, something that makes the cancellation natural rather than miraculous. This is the hierarchy problem. Why is the Higgs mass so much smaller than the Planck scale? Why is the weak force so much stronger than gravity? These are really the same question asked different ways, and nobody has a satisfying answer yet. For decades, the leading candidate for solving the hierarchy problem was something called supersymmetry. You might have heard this term. People sometimes shorten it to SUSY, which is a surprisingly cute name for such a profound idea. The basic concept is elegant. What if every particle we know about has a partner, a superpartner, that's similar but differs in a specific quantum property called spin? Quarks would have squarks. Electrons would have selectrons. Gluons would have gluinos. And here's the beautiful part. The quantum corrections from these superpartners would naturally cancel the enormous corrections from the regular particles. Not because of some miraculous coincidence, but because of a symmetry. The cancellation would be built into the structure of the theory itself. The hierarchy problem would dissolve. Supersymmetry was proposed in the early 1970s, and for a long time it was the darling of theoretical physics. It was mathematically beautiful. It solved the hierarchy problem. It provided a natural candidate for dark matter. The lightest superpartner, if it were stable, would be exactly the kind of weakly interacting massive particle that cosmologists were looking for. It even helped with something called gauge coupling unification, where the strengths of the three non-gravitational forces, if you extrapolate them to very high energies, almost but not quite converge to a single value in the standard model. With supersymmetry, they converge precisely. It was almost too good. But here's the catch. Supersymmetry predicts new particles, lots of them, and those particles should be detectable. In the simplest, most natural versions of supersymmetry, the versions that solve the hierarchy problem most elegantly, the superpartners shouldn't be too much heavier than the particles we already know. They should have masses in the range of a few hundred gigaelectron volts to maybe a tera-electron volt or so, which means the LHC should be able to produce them. And the LHC has looked very, very hard. Since 2010, both ATLAS and CMS have conducted exhaustive searches for supersymmetric particles. They've looked in dozens of different channels, with dozens of different signatures. Squarks and gluinos would be produced in pairs. They'd decay through cascades of lighter superpartners. They'd produce distinctive patterns of jets and missing energy. The experiments know exactly what to look for, and they've found nothing. Year after year, run after run, the exclusion limits have climbed higher. Squarks and gluinos below about 2 TeV are now ruled out in most scenarios. The simplest, most elegant versions of supersymmetry, the ones that originally motivated the whole program, are increasingly squeezed. They're not completely dead. There are always more complicated versions with more parameters that can evade the current bounds. But those versions tend to be less natural, less elegant, and they solve the hierarchy problem less cleanly. The beautiful simplicity that made Susie so attractive starts to erode when you have to contort the theory to hide from the data. This is one of the things that makes the Higgs mass of 125 giga-electron-volts so tantalizing and so frustrating at the same time. It's light enough that the hierarchy problem is real and pressing. But the absence of new particles at the LHC means that whatever solves the hierarchy problem, if anything does, is being very coy about revealing itself. And there's another wrinkle to the 125 giga-electron-volt story, something even stranger. It has to do with the stability of the vacuum itself. Remember the Higgs field, how it permeates all of space, how it settled into a particular value after the universe cooled? That value, the one that gives particles their masses, corresponds to a minimum in the Higgs potential energy. Think of it like a ball sitting at the bottom of a valley. The ball is stable there. It's not going anywhere. But here's the question. Is that valley the deepest point in the entire landscape, or is it just a local dip? Is there an even deeper valley somewhere else that the ball could potentially roll into, given enough of a push? This depends on the precise shape of the Higgs potential, and the shape of the Higgs potential depends on, you guessed it, the Higgs mass, along with the top quark mass and a few other parameters. When you plug in the measured values, 125 gigaelectron-volts for the Higgs, about 173 gigaelectron-volts for the top quark, and you run the calculations, including all the quantum corrections, you get a fascinating and slightly unsettling answer. Our vacuum appears to be metastable, not unstable. We're not about to wink out of existence, but not absolutely stable either. There appears to be a deeper minimum in the Higgs potential at extremely high field values, way up near the Planck scale. In principle, the universe could quantum tunnel from our current vacuum to that deeper one, but the probability of this happening is astronomically small. The expected lifetime of our metastable vacuum is something like 10 to the 100 years, which is so far beyond the current age of the universe that it's effectively forever. So don't lose any sleep over it. Well, actually, you're trying to sleep, so maybe that's the wrong phrase. But you get the idea. It's not an immediate concern. What is interesting, though, is that the Higgs mass sits right near the boundary between absolute stability and metastability. A little heavier, and the vacuum would be completely stable. A little lighter, and it might be genuinely unstable. The fact that it's right on the edge, right at this critical boundary, feels like it might be telling us something. But what? Nobody knows for sure. Some physicists see this as evidence for the multiverse, the idea that there are vast numbers of universes with different values of fundamental constants, and we naturally find ourselves in one where the values are compatible with our existence. Others find that explanation deeply unsatisfying, almost a cop-out, a way of giving up on finding a real mechanism. The debate is ongoing and sometimes heated. And then there's the question of what else the Higgs might be connected to, because the standard model, for all its success, leaves enormous questions unanswered. Dark matter makes up about 27% of the energy content of the universe, and we have no idea what it is. The Standard Model doesn't have a particle that fits the bill. Dark energy, which drives the accelerating expansion of the universe, is even more mysterious. Neutrinos have tiny but non-zero masses, and the original Standard Model said they should be massless. The Higgs mechanism, as originally formulated, doesn't quite explain where neutrino masses come from. And then there's the matter-antimatter asymmetry. The universe is made almost entirely of matter, but the Standard Model predicts that the Big Bang should have produced equal amounts of matter and antimatter. Something tipped the balance, and we don't know what. The Higgs boson might be a window into some of these mysteries. One possibility that physicists are actively exploring is that the Higgs could serve as a portal to hidden sectors, new particles that don't interact through any of the known forces, but that do interact with the Higgs field. If dark matter particles couple to the Higgs, then the Higgs boson could occasionally decay into dark matter particles, which would show up as invisible decays, events where the Higgs is produced. But its decay products simply vanish from the detector. Both ATLAS and CMS have searched for these invisible Higgs decays, and so far the results are consistent with zero, but the measurements aren't precise enough yet to rule out a small invisible branching fraction. The current upper limit is somewhere around 10 to 15%, meaning up to that fraction of Higgs decays could be going to invisible particles, and we wouldn't have detected them yet. Future runs of the LHC, and especially the high luminosity LHC upgrade scheduled to run through the 2030s, will push that limit much lower. And this brings us to something really important about where particle physics stands right now, in this moment, this era. The discovery of the Higgs boson was a triumph, arguably the greatest triumph of big science in the 21st century so far. But it also marked a turning point, because for the first time in decades, there's no guaranteed next discovery on the horizon. Before the Higgs, physicists could point to a concrete target, find this particle, or find out why it's not there. Now, the Standard Model is complete. It works. Every particle it predicts has been found. Every measurement agrees with its calculations to extraordinary precision, and yet we absolutely know, that it's not the whole story. Dark matter is real. Neutrino masses are real. The hierarchy problem is real. The answers are out there somewhere. The question is where to look. And that question has sparked one of the most intense debates in the physics community in a generation. Some advocate for building an even larger collider, a machine that could reach energies of 100 TeV, 7 times what the LHC achieves. The proposals exist. There's the Future Circular Collider at CERN, which would sit in a new tunnel roughly 91 kilometers in circumference, dwarfing the LHC's 27. There's a similar proposal in China. These machines could probe the Higgs in exquisite detail, measure its self-coupling, how the Higgs interacts with itself, which would reveal the actual shape of the Higgs potential, and tell us whether our vacuum really is metastable. They could discover heavy new particles that the LHC simply doesn't have the energy to produce. But these machines would cost tens of billions of dollars and take decades to build. And after the SSC cancellation, after the experience of promising discoveries that didn't materialize at the LHC beyond the Higgs, there's a real question about whether the physics community can make a compelling enough case. The argument isn't just scientific, it's political, economic, sociological. It's about what kind of questions a society decides are worth spending its resources to answer. Meanwhile, the LHC itself still has a long future ahead. The high luminosity upgrade, often called the HLLHC, will increase the collision rate by a factor of 5 to 10 beyond the original design. By the time it finishes running, probably sometime around 2040, it will have recorded roughly 20 times more data than has been collected so far, and with that data, physicists will be able to measure the Higgs boson's properties with percent-level precision. They'll be able to look for rare decay modes that are predicted by the standard model, but haven't been observed yet. The Higgs decaying to muon pairs, for instance, which would be the first direct evidence of the Higgs coupling to second-generation fermions. They'll search for subtle deviations from standard model predictions, tiny discrepancies that might point toward new physics lurking just beyond the edge of what we've been able to see so far. And that phrase, just beyond the edge, is really the story of where we are right now with the Higgs boson. Because finding it was never the end. It was the beginning of an entirely new kind of investigation, one that's quieter and more painstaking than the dramatic discovery moment in 2012, but in many ways, just as important. Let me explain what I mean by that. When you discover a new particle, the first thing you do is confirm it exists. Check. The second thing is you measure its basic properties, its mass, its spin, its parity, how it decays. Check, check, check. The Higgs came in at about 125 gigaelectron volts, spin 0, positive parity, decaying into the channels the standard model predicted. All consistent. But here's where it gets subtle, and honestly kind of beautiful in a nerdy way. The standard model doesn't just predict that the Higgs exists. It predicts exactly how strongly the Higgs should interact with every other particle. And those predictions are sharp. They're not vague. They're precise numerical values that depend on the masses of the particles involved. The heavier a particle is, the more strongly it should couple to the Higgs field. That's the whole point. Mass comes from the Higgs, so the coupling strength and the mass are directly proportional. A top quark, which is the heaviest known fundamental particle at about 173 gigaelectron volts, should couple to the Higgs very strongly. An electron, which is tiny, about 0.005 of a gigaelectron volt, should couple incredibly weakly. And everything in between should fall on a straight line when you plot coupling strength against mass. So what experimentalists have been doing since 2012, and what they'll continue doing through the HLLHC era and beyond, is testing that line, point by point, particle by particle. Does the Higgs couple to the top quark exactly as predicted? What about the bottom quark, the tau lepton, the W and Z bosons? Each measurement is like placing a dot on a graph, and if the standard model is right, all those dots should land precisely on that predicted line. If even one dot is off, even slightly, it means something else is going on. Something beyond the standard model is tweaking the relationship between the Higgs and that particular particle. And so far, every dot has landed on the line, which is simultaneously reassuring and a little frustrating if you're someone hoping for a crack in the standard model. But the error bars are still large enough that there's room. When you measure a coupling with, say, 10 or 15% uncertainty, you can't see a 5% deviation. You need to get those measurements down to the 1 or 2% level before you can really start to probe whether the standard model's predictions are exactly right or just approximately right. And that's precisely what the HLLHC is designed to do. It's a precision machine. The era of discovery, the big, dramatic, we found it moment, may or may not happen again at the LHC. But the era of precision is just beginning. Now, There's one particular measurement that physicists are especially eager to make, and it's worth spending some time on because it connects back to some deep ideas we talked about earlier. It's the Higgs self-coupling. The idea that the Higgs boson can interact with itself. Think about what that means for a second. Most particles interact with other particles through the fundamental forces. Electrons repel each other through electromagnetism. Quarks attract each other through the strong force. But the Higgs has this unusual property where it can interact with copies of itself, because the Higgs field's potential energy, that Mexican hat shape we talked about, isn't just a simple bowl. It has a specific curvature, a specific shape, and that shape determines how the Higgs boson interacts with itself. If you could measure the self-coupling precisely, you'd essentially be mapping the shape of the Higgs potential. You'd be confirming whether the potential really looks like what the standard model says it looks like, or whether it has a different shape that might tell you something about the vacuum metastability question, or about why the Higgs mass is what it is. The problem is that measuring the self-coupling requires you to observe events where a single collision produces two Higgs bosons at once, and these events are extraordinarily rare, even rarer than the single Higgs production that took years and trillions of collisions to observe. The rate of di-Higgs production in the standard model is predicted to be roughly 1,000 times smaller than single Higgs production. So you need enormous amounts of data, and you need to be very clever about how you analyze it. The HLLHC should be able to get a rough measurement, maybe constrain the self-coupling to within about 50% of the predicted value. To do better than that, to really nail it down, you'd probably need one of those future colliders. A machine like the proposed Future Circular Collider, running at 100 TeV, could measure the self-coupling to maybe 5 or 10% precision. That would be genuinely revelatory. But let's step back from the technical details for a moment and think about what's really happening here in the broader sweep of physics. Because the story of the Higgs, from Peter Higgs scribbling on a notepad in Edinburgh in 1964, to the HLLHC running in the 2030s, is really a story about one of the deepest questions humans have ever asked. Why does the universe have the structure it has? Why do things have mass? Why are there atoms? Why is there chemistry, biology, us? And the answer, or at least a crucial piece of the answer, turns out to involve this invisible field that fills all of space, that breaks a symmetry that would otherwise make the universe a very different and much simpler place. And here's something I find genuinely moving about this. If you'll indulge me for a moment, the Higgs field does its work silently. You can't see it. You can't feel it. You walk through it every moment of your life, and you have no direct sensation of it whatsoever. The only reason we know it's there is because a handful of theorists in the 1960s noticed a mathematical inconsistency in the equations describing the weak force, and they realized that a hidden field could resolve it. And then, nearly 50 years later, thousands of engineers and physicists built the most complex machine in human history, buried it under the French and Swiss countryside, smashed protons together at nearly the speed of light, and caught the faintest whisper of that field vibrating, a tiny bump in a histogram, a statistical excess at 125 giga-electronvolts. That's how we confirmed one of the most fundamental features of reality, through sheer stubbornness, ingenuity, and an unwillingness to leave the question unanswered. But the questions that remain are, in some ways, even more profound than the one the Higgs answered. And this is where the Higgs connects to the biggest open mysteries in physics. We talked about the hierarchy problem, why the Higgs mass is so much lighter than the Planck scale. We talked about vacuum metastability. But there are other connections that are worth understanding, because they show you just how central the Higgs is to everything we don't yet know. Take dark matter. We know from astronomical observations, galaxy rotation curves, gravitational lensing, the cosmic microwave background, that about 27% of the energy in the universe is made of something that interacts gravitationally, but doesn't emit or absorb light. We have no idea what it is. None of the particles in the Standard Model can account for it. But here's the thing. The Higgs boson might be our best window into whatever dark matter actually is. If dark matter particles interact with the Higgs field, if they get some or all of their mass from coupling to it, then occasionally a Higgs boson produced at the LHC could decay into dark matter particles. Those particles would fly out of the detector without interacting, leaving no trace. What you'd see is missing energy, a Higgs boson that seems to vanish. These are called invisible decays of the Higgs, and physicists have been searching for them carefully. So far, the data says that no more than about 10 to 15% of Higgs decays can be invisible, which already constrains certain dark matter models. But with more data from the HLLHC, that bound will tighten. If invisible decays are found, it would be one of the most important discoveries in decades. If they're not, it rules out a wide class of theories about how dark matter connects to the particles we know. And then there's the question of the matter-antimatter asymmetry. The universe is made almost entirely of matter, but the laws of physics, as we understand them, treat matter and antimatter almost identically. So how did the universe end up with this overwhelming preference for matter? One of the conditions needed to generate this asymmetry, laid out by the physicist Andrei Sakharov back in 1967, is something called a departure from thermal equilibrium in the early universe. One way this could have happened is through a strong first-order phase transition associated with the Higgs field. Remember, in the very early universe, when temperatures were extraordinarily high, the Higgs field was in a symmetric state, sitting at the top of the Mexican hat, so to speak. As the universe cooled, the field rolled down into the brim, picking a direction, breaking the symmetry. The question is, how did that transition happen? Did the field smoothly slide down, like water gradually cooling and freezing, or did it happen violently, through bubbles of the broken symmetry phase nucleating and expanding, colliding with each other, creating tremendous turbulence? In the Standard Model, with a Higgs mass of 125 gigaelectronvolts, the transition is actually smooth, not a strong first-order transition, which means the Standard Model can't explain the matter-antimatter asymmetry through this mechanism. But if there are additional scalar fields, additional Higgs-like particles that we haven't discovered yet, the transition could have been violent enough. And the way to search for those additional scalars is, once again, through precision measurements of the Higgs we already know about, and through direct searches at higher energies. You see how everything keeps coming back to the Higgs? It's like a crossroads. Every major unsolved problem in fundamental physics, dark matter, the matter-antimatter asymmetry, the hierarchy problem, vacuum stability, has a thread that passes through the Higgs sector. That's why physicists are so obsessed with measuring its properties to extraordinary precision. Not because they want to confirm the Standard Model for the 100th time, but because any deviation, any tiny crack, could be the clue that unravels one of these deeper mysteries. And this brings us to something that I think is really worth sitting with, especially as you're lying there in the dark, maybe drifting a little. The Higgs boson has taught us something remarkable about the nature of empty space itself. Before the Higgs mechanism was understood, you might have thought of the vacuum, empty space, the void, as truly empty. Just a stage on which particles move around and interact, but the Higgs field changed that picture completely. The vacuum isn't empty, it's full. It's saturated with this field that has a non-zero value everywhere, at every point in the universe. And that value is what gives particles their masses, what determines the strengths of forces, what shapes the very structure of matter. The vacuum is not nothing, it's something. It has properties. It has energy. It might even be unstable, sitting in a local minimum that could someday tunnel to a deeper one. The ground beneath our feet, metaphysically speaking, might not be as solid as we think. And that's a strange and beautiful thought, isn't it? That emptiness has structure, that the nothing between the stars, the silence between atoms, is humming with something that matters. Literally matters, in the sense that it's what makes matter possible. Let's stay with that for a moment. Because I think at the end of all this, after the equations and the colliders and the Nobel Prizes and the decades of searching, this might be the deepest thing the Higgs has given us. A new understanding of what nothing really is. You know, the ancient Greeks argued about the void. Democritus thought atoms moved through empty space. Aristotle said, no, nature abhors a vacuum. There's no such thing as true emptiness. And for most of the history of physics, people went back and forth on this. Newton imagined absolute space as a kind of fixed, invisible stage. Then came the luminiferous ether, this hypothetical substance that was supposed to fill all of space and carry light waves the way air carries sound. And when Michelson and Morley couldn't detect the ether in 1887, when Einstein's special relativity said you didn't need it, people breathed a sigh of relief and said, okay, space really is empty. There's nothing there, just geometry. But quantum field theory brought the ether back in a way. Not as a material substance, not as some wind you can measure your speed against, but as something subtler and honestly stranger. The quantum vacuum is seething with fields. Every kind of particle has a field that permeates all of space, and those fields are never perfectly still. They fluctuate. Virtual particles pop in and out of existence on timescales so short that the uncertainty principle allows it. The electromagnetic field has zero-point energy even in its ground state. And the Higgs field, uniquely among all the fields we know about, has a non-zero value in that ground state. It's not fluctuating around zero. It's settled at a specific, non-zero expectation value, about 246 giga-electron volts if you want the number. And that number, that value, is one of the most consequential quantities in the universe. It sets the mass of the W and Z bosons. Through the Yukawa couplings, it sets the mass of every quark and every charged lepton. It determines the range of the weak force. It shapes the periodic table. It decides how nuclear fusion works in stars, which determines what elements get made, which determines whether chemistry happens, whether planets form, whether you exist. 246 giga-electron volts. That's the number the universe chose, and we have no idea why it's that number and not some other number. That's one of the open questions. The standard model doesn't predict it. You just measure it and plug it in. But everything flows from it. So the vacuum is this enormously structured thing. It's not a blank canvas. It's more like, imagine a crystal. A perfect crystal has a very specific internal arrangement, and that arrangement determines how vibrations travel through it, what kinds of excitations are possible, how it responds to stress. The vacuum is like that. The Higgs field's non-zero value is like the crystal's lattice structure. It breaks the underlying symmetry and creates the specific pattern of masses and forces that we observe. If the Higgs field had settled at zero instead, the universe would be symmetric in a way that's mathematically elegant but physically barren. All the particles that get mass from the Higgs would be massless. Electrons would fly around at the speed of light. They wouldn't bind to nuclei. There would be no atoms, no chemistry, no structure, just a hot soup of massless particles streaming past each other forever. And if the Higgs field had settled at a different non-zero value, say twice as large, the masses of all those particles would be different. The proton might be unstable. Nuclear physics would change. Stars might not work. Or they might work differently, making different elements. The universe would be a completely different place. This is what physicists sometimes call the landscape problem, or the fine-tuning problem. And it connects to some of the deepest and most contentious questions in modern physics. Why these values? Why this vacuum? Is there a mechanism that selects them? Some deeper theory that predicts the Higgs field's expectation value from first principles? Or is it, and this is where it gets philosophically uncomfortable for some people, is it just one of many possible values, realized in one of many possible universes, and we happen to find ourselves in this one because it's one of the ones where observers can exist? That's the anthropic argument, and it's genuinely controversial. Some physicists, like Steven Weinberg, have used anthropic reasoning productively. Weinberg actually used it in 1987 to predict the rough magnitude of the cosmological constant before it was measured, which is remarkable. Others, like David Gross, have argued that anthropic reasoning is a kind of giving up, a retreat from the goal of finding a unique predictive theory. It's one of those debates where very smart people disagree very strongly, and it's not resolved. The Higgs boson sits right at the center of it, because the Higgs mass, 125 gigaelectronvolts, is one of the values that seems uncomfortably fine-tuned if you take the Standard Model seriously, all the way up to very high energies. Remember the hierarchy problem we talked about earlier? The fact that quantum corrections should push the Higgs mass up to something enormous, and yet it sits at this modest value? That tension is real, and the fact that the LHC hasn't found supersymmetric particles or any other new physics to explain it has made the tension sharper, not softer. So where does that leave us? Well, it leaves us in one of the most interesting periods in the history of fundamental physics. And I don't mean interesting in a comfortable way. I mean interesting in the way that the late 19th century was interesting, when classical physics seemed nearly complete, but there were these nagging little problems: the ultraviolet catastrophe, the photoelectric effect, the stability of atoms, that turned out to be cracks in the foundation, cracks that would eventually split open into quantum mechanics and relativity, and a completely new understanding of nature. We might be in a similar moment. The Standard Model works. It works spectacularly well. Every prediction it makes, when we can calculate precisely enough to test it, comes out right. The Higgs boson was its last missing piece, and finding it at 125 gigaelectronvolts with properties consistent with predictions was a triumph. But the Standard Model also has these glaring holes. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't explain why there's more matter than antimatter. It doesn't explain the pattern of masses and mixing angles, why the top quark is so heavy and the neutrinos are so light, why there are 3 generations of matter particles and not 2 or 4. It has about 20 free parameters that you just have to measure and input by hand. It's not a final theory. It's an extraordinarily successful, effective theory, a description that works beautifully at the energies we can probe, but that almost certainly breaks down or gets subsumed into something larger at higher energies. And the Higgs sector is where the cracks are most likely to show. Because the Higgs is the least understood part of the Standard Model. We've known about quarks and leptons and gauge bosons for decades, and we've measured their properties to extraordinary precision. The Higgs is new. We've only been studying it directly since 2012. Our measurements of its couplings are still relatively rough, 10, 15, 20% precision in many cases. Its self-coupling, which tells us the shape of the potential, is essentially unmeasured. We don't know if there are additional Higgs bosons. We don't know if the Higgs is truly elementary, or if it's composite, made of smaller constituents bound together by some new force, the way protons are made of quarks. There are models, Technicolor models, composite Higgs models, that propose exactly that, and they're not ruled out yet. So the next few decades of particle physics are, in a very real sense, the era of the Higgs. The high luminosity LHC, which should be running through the 2030s, will accumulate roughly 20 times more data than the LHC has collected so far. That means 20 times more Higgs bosons produced, which means much more precise measurements of its couplings, better sensitivity to rare decay modes, and the first real shot at measuring the self-coupling, even if only roughly. Beyond that, proposals for future colliders, the FCC at CERN, the CEPC in China, the ILC in Japan, a muon collider that's still in early conceptual stages, these would be Higgs factories, producing millions of Higgs bosons in clean environments and measuring its properties to sub-percent precision. At that level of precision, you'd be sensitive to the subtle quantum fingerprints of new particles that are too heavy to produce directly. You'd be looking for ghosts, essentially. The faint shadows that heavy, undiscovered particles cast on the Higgs boson's behavior through virtual quantum corrections. It's a beautiful strategy when you think about it. You can't always find new things by smashing harder. Sometimes you find them by measuring more carefully. It's like astronomy. You can build bigger telescopes to see fainter objects farther away, or you can point your existing telescope at a nearby star and measure its wobble so precisely that you detect the gravitational tug of an unseen planet. Both approaches work. The Higgs, in this analogy, is the nearby star, and we're watching for wobbles. And here's something I find quietly astonishing. The Higgs field is the only fundamental scalar field we've ever discovered. Every other field in the Standard Model is either a spin 1/2 fermion field, quarks and leptons, or a spin 1 gauge boson field, photons, gluons, W and Z bosons. The Higgs is spin 0. It's the only one. And scalar fields have a special place in physics because they're the simplest kind of field, and because they can do things that other fields can't, like having a non-zero value in the vacuum without breaking Lorentz invariance, without picking out a preferred direction in space. That's why the Higgs mechanism works. A spin 1 field can't fill the vacuum uniformly without choosing a direction. A scalar field can. It's isotropic. It's the same in every direction. It fills space like a perfectly still pond. And because of that special property, scalar fields show up in all sorts of theoretical contexts beyond the Standard Model. The inflaton, the hypothetical field that drove cosmic inflation in the first fraction of a second after the Big Bang, stretching the universe by a factor of at least 10 to the 26 in a tiny sliver of time. That's usually modeled as a scalar field. Some models of dark energy use scalar fields. The axion, hypothetical particle that could solve the strong CP problem and might be dark matter, is associated with a scalar or pseudoscalar field. So finding one real scalar field in nature, the Higgs, gives us confidence that scalar fields aren't just mathematical conveniences. They exist. Nature uses them. And there might be more of them out there, playing roles we haven't identified yet. That thought, that the Higgs might be just the first scalar field we've found, the tip of an iceberg, is one of the things that keeps physicists up at night. In a good way. In the way that a really compelling mystery keeps you turning pages. But you don't need to turn any more pages tonight. You've come a long way. From the simple question of why things have mass, through quantum fields and broken symmetries and superconductors and enormous underground tunnels and detectors the size of cathedrals, all the way to the edge of what we know and the beginning of what we don't. The Higgs boson is real. The Higgs field is real. You are right now lying in a bath of it. It's giving the electrons in your body their mass, which is what lets them orbit nuclei, which is what makes atoms possible, which is what makes you possible. The field that Peter Higgs and Francois Englert and Robert Brute and Gerald Guralnick and Carl Hagen and Tom Kibble wrote about in 1964. The field that Steven Weinberg and Abdus Salam wove into the electroweak theory, the field that Gerard 't Hooft proved was mathematically consistent, the field that thousands of physicists spent decades building machines to test. That field is here, in this room, in the space between your thoughts. And it's doing its quiet work, as it always has, since a fraction of a second after the beginning of everything. Giving structure to the void, making the universe not just possible but particular. This universe, with these masses, these forces, these atoms, these stars, this you. The vacuum hums with it, steady and silent and everywhere. And you're part of it, and it's part of you. And that's a good thought to fall asleep to. The deepest layer of reality, the thing that makes matter matter, is right here. It's always been right here. And tomorrow, or next year, or next decade, someone will measure it a little more precisely, and maybe, just maybe, they'll find a crack, a wobble, a whisper of something new. But that's a story for another night. For now, just let the field hold you, the way it holds everything, gently and invisibly and without fuss. The way the ground holds the ocean, the way silence holds a song after the last note fades. You're here. The field is here. And that's enough.